Hey folks, welcome back to another lecture in the Introduction to Earth Sciences with Dr. Matthew Wielicki lecture series here on YouTube. I am Dr. Matthew Wielicki. Thanks for joining us. If you have a chance, please follow me on Twitter at Matthew Wielicki and subscribe to my Substack, irrationalfear.substack.com. So this is lecture 10 in what's going to be a 19-ish or 20-ish part series. Today we're going to talk about deep time. We'll talk about both how that correlates in terms of the geologic past, also how we can tell relative time, so we can date objects that are kind of relative to each other. This one's older than the other. And then how do we get absolute time, where we can actually say, well, this rock or this mineral is this many millions of years old, for example. The image in front of you now is the lab that I did my PhD in. I spent many nights in that lab, sleeping in that lab. Those are two secondary ion mass spectrometers. There's a newer one in front of you, and then if you can kind of look into the back of that image, you can see in the background there's another one. Two very similar instruments, both what we call secondary ion mass spectrometers. These are these very expensive, fancy pieces of equipment that allow us to use radioactive decay to identify the age, the absolute age of something. And we'll talk about that in the latter part of this lecture. So we have to remember a few key principles. The principle of uniformitarianism. So this principle states that essentially the present is the key to the past. So for example, today where we find ripple marks like you see in the image on your left are usually associated with water flowing. If they're symmetrical, it's usually in areas that have tidal influences where water flows in one direction for a little while and then the other direction for a little while. And you get these nice symmetrical ripples. Well, if we find those ripple marks in ancient rocks, for example, that's a 150 million year old sandstone here in Colorado where I am today. In the image on your right, we can safely assume that that environment was probably pretty close to what we see happening in today. So again, the present is the key to the past. We also have to make an assumption of original horizontality. So this is the principle that sediments are essentially deposited in horizontal layers. So we've talked about this a little bit already when we talked about sedimentary rocks. It's very difficult to put loose sediment on a steep slope. And the next time it rains or the next time you have a big wind event, that material moves down slope and it eventually settles in some relatively horizontal place. And then eventually, in order to make a rock, you have to bury that material. And so in order for it to get buried, you have to pile more material. And so you tend to do this in relatively horizontal places, the bottom of valleys, for example, as opposed to the slopes of a mountain. So this is the principle of original horizontality. Also, the principle of superposition. So remember we talked about this. This essentially states that in a relatively undisturbed sequence of rocks, the material at the bottom is older than the material at the top. So nature really doesn't just have a way of kind of opening this pile of sediments and slipping in some sediments in between layers. It just kind of settles on top and starts to get buried and eventually compacted and becomes another layer. And so older stuff at the bottom, newer stuff at the top. And so those are principles that we've already covered when we've talked about other rock types and other situations. So when we start talking about dating and time in terms of geology, you're going to see, as I just mentioned a little bit ago, we're going to talk about it in two distinct groups. We're going to talk about relative age dating. So here's an example of two layers, and layer A is relatively younger than layer B. I'm using the principle of superposition to do that because A is above B. I know that A should be relatively younger than B. But notice I'm not assigning any numbers here. I don't really know how much younger, but I can safely say that it's relatively younger than the layer below it. So that's relative dating. That's very different than, for example, numeric dating or absolute dating. Here I can say layer A is 15 million years old and layer B is 20 million years old. And so not only do I know that layer A is relatively younger than layer B, but I know that it's 5 million years younger. So this is a lot more information. So this was always the holy grail, but it wasn't until the technological advances of the mid 20th century that we got the instruments that allowed us to actually get to the point where we could talk about this. And we'll talk about this in the second half of the lecture. So relative age dating, right? This is the age. This is dating one feature with respect to another, as opposed to numerical aging, which is actually a specific numerical age or an absolute age for a feature. So the principles for relative dating, we've already talked about a few of them. We just reviewed 3, but we're going to talk about 4 new ones that we haven't discussed yet. The first is the principle of original continuity. And so this just essentially means that if we find layers that are separated by, for example, a canyon where there's a river, we can safely assume that those layers were probably continuous at one point and have subsequently been eroded away and then carried off. And so, for example, if we're looking at some layers like this is in the Southwest where you have these beautiful sandstone kind of monoliths that exist, we can safely assume that these was probably a large continuous layer and that material has been subsequently removed, as opposed to just little bits of this same sandstone being deposited across these features. Another principle that is new that we're going to use to figure out the timing of things is cross-cutting relationships. And cross-cutting relationships is essentially the principle that the relative age of a rock can be determined by looking at which rock or structure cuts another. And I like to use the analogy of a piece of paper and some scissors. In order for the scissors to cut the paper must already exist. And that can be said that the feature that has been cut, the paper, must be older than the thing that's doing the cutting, right? And so if you have a situation where you have, for example, a magma chamber coming in and it's cooking rocks all around it, well, that magma chamber must have come after the rocks. The rocks that are being cooked by the magma must already exist in order for the magma to actually cook them. Or if a fault comes through, like you see in the upper right, number 2, if a fault comes through and cuts all that material must have already existed in order to have been cut by the fault. A fault can't cut material that doesn't exist. And so if the fault is cutting that magma that is now cooled, and we would call that a pluton, if you need a reminder of that, go back to the chapter when we talk about igneous rocks, that because that fault is cutting the pluton must have existed. And thus, the fault must have come after the pluton. So these are known as cross-cutting relationships. Here's an example of a cross-cutting relationship. We looked at this picture when we talked about what type of fault this was. Remember, this was a normal fault. Remember, footwall up normal. If you took that little person and you just kind of elevated them up, made them kind of hover in the air such that their head and their feet, their body was being cut by the fault, right? Their head would be on the left-hand side. We would call that the head wall or the hanging wall. Their feet would be on the right-hand side block. That would be the footwall. The footwall is going up, so this is a normal fault. But also something that I know is that those layers that are being cut by this fault must have existed for that fault to actually cut them. The fault can't cut layers that don't exist. Here's another cross-cutting relationship where there's a magma that's intruding across a bunch of layers. We know that those layers must have existed prior to that magma coming in and cutting through them. Otherwise, that magma would have just spilled out on the surface and spread out. It wouldn't have come out and stayed in this little crack. That crack was cutting through these layers, and that magma exploited it. So that magma is younger than the layers that it's cutting across. We can also talk about baked contacts. So this is another physical principle that helps us figure out a relative age. And this is where a hot magma actually bakes the wall rock that is containing it. So because magma by definition is very hot, again, go back to igneous rocks if you need a refresher, that material is so hot it actually bakes the wall rock that it's holding, and we call those baked contacts. Again, if you see a baked contact, you know that that material that is being baked must have existed, and then that magma intruded and then baked that material. Here's a baked contact that we talked about when we talked about metamorphic rocks. On the bottom right, that's kind of cutting down into the road, that used to be a magma. It was very hot when it was intruded into these rocks. You can see that right where the magma was touching the wall rock, you have these very dark rocks. That's the baked contact. As you go away from what used to be this very hot magma, you can see you get cooler and cooler. The colors change, and eventually you get into rocks that essentially didn't feel any temperature change from this magma. Another principle that we can use to do relative age dating is inclusions. So I like to use the analogy of making some chocolate chip cookies. You're going to make your dough, and then you're going to put the chocolate chip cookies. The chocolate chip cookies already existed. The chocolate chips already existed, right? The chocolates. You buy those in a bag. You make your dough. You dump those in, and the chips that are included in there are older because they were made in some factory somewhere you bought them than the dough that is holding them. Right, so in the picture that we see on the left, we see that there's some sediment on top of what we call a flow, a basalt, so that's a lava flow. We can see that that sediment has little bits and pieces of that lava flow. That tells us that the lava flow must have existed, and then when the sediment came in and filled in on top, little chunks of the lava flow got entrained in there. On the picture on the right, we again have a lava flow, but this is now a sill. This is an intrusion. It's squeezed between two layers, and we know it's squeezed between two layers because we can see little bits of the layer on top and little bits of the layer on bottom included in this now igneous sill, this basalt. And so those two layers must have existed for little bits and pieces of them to fall into this hot magma as it was splitting in between these layers and eventually cooling and entraining and including, having these inclusions of these other rocks. Here's an example of an inclusion. This we call a xenolith. We haven't really drilled down into the mantle of the Earth. There's actually some projects now that are getting close, and there has been some claims that we may have actually approached the crust mantle boundary. But we have good evidence of the mantle because we have these xenoliths that come up where we have these really deep-seated volcanism. Little bits of the mantle get entrained into this volcanism and they come up to the surface as inclusions. And we know that that material must be older than the lava that is holding it because it never actually melted. It just got picked up and included into the lava and eventually brought to the surface. It's a wonderful little bit of nature that brings up these little pieces for us to investigate such that we don't have to drill down much deeper. If we remember in the very first lecture, we talked about the deepest we've ever drilled on the planet is about 12 kilometers. So all of this relative dating allows us to look at a real complex image like this and start to parse it out into essentially what happened when. And the way we do that is we use all of those principles that we just discussed in trying to parse things out. So let's go through this, what looks as a pretty complicated image, and try to put things into relative order from oldest to youngest. So what happened first? Well, first we know that by using the principle of original horizontality, that these layers must have been laid down flat. There's no way that we can lay these layers down in this bent, in this kind of folded, you can see an anticline on the left and a syncline on the right. We talked about that in the last lecture. And so they just wouldn't happen like that. The sediment would have collected in the valleys and would have been stripped off the peak. And so these layers must have been at some point laid down horizontally. And then we can also apply the principle of superposition to safely assume that the bottom layer, the one with the 1 at the bottom, is the oldest, and the layers on the top are the youngest. We use the principle of superposition for that. And then we can see that there's a sill. That sill has been intruded in between layers 4 and 5. I know it must come after layer 4 and 5 have formed because little bits of layer 4 and little bits of layer 5 are included into the sill. And so I'm going to use my principle of inclusions to make the assumption that those two layers, 4 and 5, must have been there, and then the sill came in. Now, it's hard for me to know anything about layers 6, 7, and 8, so there is a little bit of gray area here, but I'm just going to put it after these other layers had formed. The sill intruded in and has little bits of 4 and 5. Then subsequently, there was some sort of tectonic change. There was compression because we can see the folding that has happened. We can see the anticline on the left and the syncline on the right. So we know that that is compression. You can't fold things through tension. Pulling things apart doesn't actually create folds, only pushing things together. And so we know that this folding must have happened after the sill because the sill is also equally bent or folded as the other layers. So the sill couldn't have come in after. It must have actually been intruded in, and then the folding event occurs. We know the magma must come after because the magma doesn't appear to be folded. but it appears to have cooked all of the other layers. So if we look, we can see this kind of shading in the upper right image, this little bit of darkness around, and it has in the middle of the image, it says baked contact. So we're going to use that principle, and we can see that every layer is baked. There is no layer that isn't baked, and so all of those layers must have existed. The magma chamber, the Pluton doesn't appear to be folded, so everything probably existed and was folded, and then the igneous rock came in and baked everything. Subsequently, there was a fault that came through. I know that fault must have come after because it appears to have cut the magma chamber. It cuts all the layers and the magma chamber as well, the granite Pluton that is now cooled. And then it appears that a dike has come through because the dike is cutting the fault. Notice that the fault doesn't have any effect on the dike. So we know that when the fault came through and shifted all these rocks, the dike must have not existed. Otherwise, it too would have been shifted. And so the dike comes through and cuts across after. And then eventually there's some erosion at the top. And so what we've taken is we've taken a image like this. This is something that I would have my students do in an exam. And we essentially have put this into order of oldest to youngest in a relative framework that makes sense. But notice we haven't really assigned any numbers to anything. We haven't put anything into context in terms of numerical or absolute ages. We're just saying that, here is a hypothetical scenario in which you would end up with this relatively complicated package, and all of these events make logical sense. It doesn't necessarily mean it exactly happened that way. There's a little bit of gray area here, but this is one of relatively few scenarios of how you'd end up with a package like that. So that's really important information if you're a geologist or you're exploring for energy resources or mineral resources. It's really important for you to know when certain rocks were laid down compared to when others were, if these rocks were cooked because there was magma intrusions, or did they come in subsequently to that. And so this is all really important information. But ideally, this isn't nearly as useful information as being able to absolutely date each of these. Another principle that we use when we're doing relative dating is we look at the life on the planet. And it's unfortunate, but it's true that 99% of the species on the planet have gone extinct. And so everything survives on the planet for a certain amount of time and then goes extinct. And what that means is that if you can find certain flora and fauna, fossilized flora and fauna, and you know the time period when those things existed on the planet, then you have essentially determined a relative time period now when your rock layers were put down. For example, if you find a certain shell or trilobite fossil, trilobites existed something on the order of 150 to 300 or so million years ago. You know that if you find these trilobite fossils, well, your rocks were laid down at some point between those two time periods. And this is known as the principle of fossil succession. So this is really important in getting away from just having relative dating to starting to move towards getting more numerical dates. And unfortunately, there's just no place on the planet that has a package of rock that gives us all the information that we need. We're always going to have missing bits of time. And you can just imagine little chunks of the clock that are missing, because really these layers of rock are how we are figuring out the history of the Earth. And if we're missing layers of rock, then we're missing information. We call those missing bits of information unconformities. So you can see a package of rock like this and it looks nice and uniform and everything is laid down flat. But if you actually went and dated these rocks, and we'll talk about this in a few minutes, how you do this, what you'd find is that there's a bunch of time missing. And so there's these time periods where there was either no rock was laid down here, or maybe rock was eroded, changes in sea level, who knows what the reason was. But there was no rocks laid down. And if there's no rocks laid down, then we don't have the information. It's because it's the rocks that are giving us the information. So these are gaps in the record, and we call these unconformities. Here's an example of an unconformity. So in the image to your right, these are rocks from Europe. In the bottom, you can see that there's rocks that are of 425 million years or so age. And above them, there is some sandstones that are 345 million years of age. And so where those two layers meet, there's about 80 million years of missing time. And so this would be called an unconformity because we're missing this 80 million years. And unconformities come in three flavors: angular unconformities, nonconformities, and disconformities. But before we discuss unconformities, we need to talk a little bit about how the planet changes, how environments will actually shift from environments of erosion to environments of deposition. And this can happen through things that we've already talked about, like tectonicism, right? So mountain building, uplift of rock. This can change. This can come on through things like climatic changes, where sea levels change dramatically. An area that used to be exposed, was subaerial and was eroding away, can now be actually under a few meters of water as sea levels change, and now it's a depositional environment, what used to be an erosional environment. And so we have this shifting back and forth as things change on the planet. And so in every location that we look at on the planet, it looks like this happens quite often. And so this is one of the reasons that unconformities are so prevalent, is because it just doesn't appear that there's a place on the planet that has stayed in, for example, a depositional environment for billions of years, such that we would have rock sequences that would go back billions of years. So it's just something to keep in mind, that we're always going to have these unconformities. There's always going to be missing time. And one of the ways we're going to get around this is we're going to start to piece together bits of information from lots of locations all around the planet, such that we can fill in these gaps in time, or these pages, these missing pages in the book of the history of the Earth. So here's some of our three examples of unconformities. So here's an angular unconformity. So imagine in time one on the left, you have this folded sequence of rocks. Sea level is relatively low, so we have this is an area that is above sea level, so it's being eroded, and it's eroded over time. You can see now in time two, the erosional surface is there. Let's imagine that sea levels rise such that now this is under a few meters of water. That water will start to deposit material, and so you start to get these nice flat original horizontal layers deposited, and you have what's known as an angular unconformity. The rocks and the layers below the dark line on the picture on the right are angled. They have folds to them. The sediment above the line is flat. This is known as an angular unconformity. And I know I'm missing material at that black line. What am I missing? Well, I'm missing all the material on the left in picture time one that was stripped off the surface. That's material that is giving me some information about what's happening about that time, and it has subsequently been stripped away, right? And so this is that missing time that we're talking about. Because these sediments or these layers are at different angles to each other, we call this an angular unconformity. Here's an example of an angular unconformity. You can see these relatively flat laying rocks on top of these highly tilted laying rocks below. Where they meet is an angular unconformity. A nonconformity is another type of unconformity. This is one where we have sedimentary layers that are on top of either igneous rocks or metamorphic rocks. So let's imagine this scenario again. So sea level is relatively low. We have some sediments that have been laid down onto some igneous rocks. In our image number one, you can see those sediments are nice and flat because of the principle of original horizontality. And because this sea level is relatively low, this is an area that is above sea level, so it's being eroded away, and you can see that it's eroded down to that level. Sea level rises, and we start to get sediment being deposited directly on top of this igneous rock, this igneous intrusion. And that dark line in image 3 on the right is our nonconformity. This is sedimentary layers that are now being laid down on top of either igneous or metamorphic layers. In this case, these are igneous, and we're missing information. What are we missing? Well, we're missing all of those layers that were that exist in the image on the left in time 1. All those layers have been stripped off, deposited somewhere else, and now new material is being deposited. So I'm missing information. And because it's sediment deposited onto igneous or metamorphic rocks, we call this a nonconformity. Here's an example of a nonconformity from the Grand Canyon. So this Colorado River is just out of your image below this image. That's the Vishnu schist at the bottom underlying metamorphic rock. And then there is overlying sedimentary rock on top of that, nicely relatively flat as the Grand Canyon sediments are. And that's a nonconformity where that sediment is touching onto the Vishnu schist, the metamorphic rock. Our last type of unconformity is a disconformity. This is an unconformity that exists between two parallel sedimentary sequences. So let's again go through our situation. You can imagine time 1, image on the left. We have relatively high sea level stand, so we're in a depositional environment. Layers are being put down, but sea levels drop because we go into a glacial period. So in a glacial period, the water gets removed out of the ocean and locked up in ice sheets and glaciers, so sea levels drop. And now we're in an erosional environment. And notice now we've stripped off that upper light tan layer, and sea levels change, climate changes, the glaciers melt, the water flows back into the oceans, and the oceans rise, and we go back into a depositional environment. Everything is relatively parallel to each other, but we're still missing information. So this is another type of unconformity. And here's one in formations in China. And these are formations that you can see have something like 220 million years of missing information in between these two layers. But you can't really tell in terms of angle or anything like that. So remember, I want to drive this point home, that no single location on Earth contains a complete record of Earth history. So these are like pages in a book. The sedimentary layers are like pages of history, and there's just chapters missing everywhere. So this is a beautiful image of the Grand Canyon. The Grand Canyon has huge amounts of missing information. I'll show you in a second. And so we have to travel around and try to piece together all this information from lots of different places. And so here's an example of a stratigraphic column collected from a beautiful location. This is the north rim of the Grand Canyon. And if you ever had a chance to go, I really encourage you. The white layers on top there are the Kaibab limestone. And you can see all these beautiful layers as you go down, and eventually the very bottom layers where the Colorado River is actually cutting down today is in the Vishnu schist. This is a metamorphic rock that is over 1 billion years old. And so we look at this and it looks like this nice, beautiful sequence of rocks. It looks like it's very homogeneous. But as you start to think about the ages of these, you'll see that there's a lot of missing information. And so here are the ages of these rocks. So this is a stratigraphic column. This is a cross-sectional diagram, and it shows you ages on the right. And so notice that we have sequences of rock like the upper portions that include the Kaibab limestone. These things are on the order of about 250 million years or so old. We have some rocks that are about 500 million years old. We have some rocks that are about 750 million years old. We have the Vishnu schist that's older than 1.5 billion years. But we are missing tons of rock. Even though it doesn't look like it, there's quite a lot of unconformities in the beautiful Grand Canyon sequence. And so we have to go fill those pages of the book in from other places. When we talk about stratigraphic columns, we draw them up in these nice kind of cartoon figures that show us kind of how the layers are look throughout. Where the layers touch, we call that a contact. That's the boundary between two formations or two layers. Where we have lots of different locations that we're trying to figure out now. So because every location doesn't have all the pages of the book, we're going to try to correlate across long distances. And we're going to use a few different methods to correlate our rocks. We're going to use lithologic correlation. So that's trying to essentially match the rock types. Do the formations look the same? Do they have the same mineralogy, geochemistry, isotopic signatures? Do the rocks essentially look the same? Are we looking at similar rocks? And we're going to do fossil correlation. We're going to look across long distances and say, I don't exactly know when the rock layer that I'm looking at over here was laid down, but both of my rock layers have similar fossils. And that should be evidence that my rock layers were laid down at similar time periods, even though they may be thousands of kilometers apart. If I'm finding fossils of similar morphologies and similar species, I can safely assume that those rocks must have been laid down at similar time periods, right? So this would be the method of fossil correlation. And occasionally we have what are known as index fossils. Now, index fossils are these wonderful pieces of information because index fossils are little buggers that had a really wide distribution, meaning they lived in lots of environments on the planet, and they had really rapid evolutionary trends, meaning their geomorphology was changing pretty quickly. So they didn't really look the same. They only kind of looked a certain way for short time periods. These index fossils are incredibly useful because if we can identify these index fossils, we have now a narrow time window of when this bugger existed, and we can be pretty safe in assuming that our rock layers were laid down in this narrow window. It's great if we had beautiful Grand Canyons everywhere, and the rocks were exposed to us like they are in the Grand Canyon thanks to the Colorado River. In most places, though, we don't have that the word's escaping me, that benefit. We have to do other things. And so what we do in a lot of places where we don't have these large canyons is we use drill cores. But essentially the principles are all the same. Instead of seeing this nice canyon wall exposed to us, we're going to see this nice drill core exposed to us, but we're still going to have a good idea of what the layers look like, and we can start to piece together and tie layers together by doing these correlations, whether lithologic correlations or fossil correlations. And we can start to piece together how these layers look and eventually how the subsurface looks. And the subsurface is really important if you want to, for example, identify where mineral deposits are or energy and energy resources. So we want to understand the subsurface, and essentially putting these stratigraphic columns together and doing these correlations is very important. Ultimately, we would love to create a geologic column. This would be a composite stratigraphic chart for the entire Earth history, the last 4.56 billion years. Right? And again, no one place will do this, but if we get enough locations, we can start to piece things together. And so people have tried to do this. And as we do this, we start to divide the geologic column into segments of time. We're going to get into this a little bit more in the next lecture, but we're just going to introduce it now. So the largest subdivision of time in Earth history we call an eon. An eon, we have 4 eons on the geologic column. So we have the Hadean, the Archean, the Proterozoic, and the Phanerozoic. Notice that those last 2 have the ending zoic. Zoic means life. Phanerozoic means visible life. Proterozoic means first life, although we actually now know that we have evidence of life in the Archean and possibly even in the Hadean. The eons are divided into eras, and the eras are divided into periods, and the periods are divided into epochs. This is going to be way more information than we need, but I do like to focus on a few of the eons and a few of the eras, so I just like to introduce it, and you'll see anytime that we have some of these graphics, there'll be periods and epochs. That just means that we have enough information to actually splice these things up into smaller time periods, but we're not going to go into any of those details, and the naming there can get a little difficult. Sometimes it's named for the location, like the Devonian. That's the representative sample for that time period is in Devon, England. Sometimes it's named after something that it contains a lot of. So the Carboniferous time period, for example, is a time period where a lot of our coal deposits existed. We'll talk about this a little bit more when we talk about climate, but that's a time period where plants were the most successful ever on the planet, and the atmospheric carbon dioxide concentration was on the order of about 12 to 1400 parts per million. So anyway, we're going to focus on the eons and the eras. We won't talk much about the periods and the epochs. We're going to get into, in the next lecture, talking a lot about the Phanerozoic. You'll see that it's split into the Paleozoic, the Mesozoic, and the Cenozoic. That just means ancient life, middle life, and recent life. Remember, Zoic means life, Phanerozoic means visible life. I focus a lot on this when I talk on social media, because the Phanerozoic is this time period of visible life. And when we talk about climate, this is what we'll talk a lot about, how the climate has changed over the last 550 million years. And you'll see that it's pretty clear that the flora and the fauna on the planet do best during warm periods and struggle during cold periods. If you Google the geologic column, you'll find things like this. Obviously, there is no exam because this is just a lecture series, but it gets pretty complicated. And so, this is great to get into detail, and we can discuss this more. Notice that there is no Anthropocene at the top. That has not been an accepted name, even though there's some prominent climate scientists that are trying to push a new time period after the Holocene, known as the Anthropocene. So far has not been accepted by any of the organizations that approve these names, but this can get pretty complicated. So over just about the last 70 or so years, technology has allowed us to move away from just relative dating, even though we're getting pretty good and we can actually get into some, having some time spans. We can now start to actually really put a number onto a rock or a mineral. We can actually determine the absolute or the numerical age, and this is through the discovery of radioactivity. And the process of doing this through is known as radiometric dating or isotopic dating, and the study is called geochronology. And my position my expertise is essentially in geochronology. I was a geochronologist. Much of what I did was people would come and work with me while they were trying to figure something else out, some other problem in earth science, and I would help them to determine the age of the sediments or the rocks that they were looking at. So just a refresher, remember we talked about isotopes. Isotopes are different versions of a same element. For example, carbon, we'll use carbon as an example. So they will have the same atomic number, but they're going to have different atomic weights. That means they have the same number of protons, but a different number of neutrons. Remember, if you change the number of protons, you change the element. Some of these isotopes are stable, meaning they're just pretty happy. But some are not stable, meaning that they're radioactive. And so they will actually go through a very complex decay process sometimes it's relatively simple. And we know that that decay has a relatively constant rate to it. And so we're going to take advantage of this radioactive decay, these isotopes that are unstable, as little clocks. So what's radioactive decay? So radioactive decay is the process by which an atom undergoes fission. Fission is the opposite of fusion. Fission means to break apart or to release particles. Fusion means to come together, to put things together. Remember, stars are doing fusion. We talked about this when we talked about how elements are formed. But when we're talking about radioactive decay, we're talking about usually larger isotopes that are breaking apart. So these are fizzing. And when we discuss this, we talk about a parent isotope and a daughter isotope. So the parent isotope is the unstable isotope that is ready to decay, and the daughter is the product of the decay of that parent isotope. Usually when we talk about radioactivity and geochronology, we talk in what we call half-lives. Half-lives is just a term that was chosen to make it easier to understand how this process works. Half-life means the time it takes for half of a group of radioactive elements, the parent, to decay into, for example, the daughter. So here is an example. Let's use the example of 5,000 years as a half-life. So imagine that we start on the left-hand side, and the green blocks are parent, so that's the unstable radioactive isotope, and the blues are the daughter, that's the stable isotope that the parent eventually decays into. We start with 16 parents and 0 daughters. We go through 1 half-life. We lose half the parent, so we go from 16 to 8, and we add those. We have to take those parents and turn them into daughters, so we go from 0 to 8 on the daughter side. So notice we have a ratio of 1 to 1. Then if we go through another half-life, so now we're at 10,000 years, we have a ratio of 1 to 3, and then we have a ratio of 1 to 5. And then we have a ratio, 1 to 7. And then we have a ratio of 1 to 15. And so you can see that the ratio of the parent to daughter tells you something about the number of half-lives. You could plot that as well. So you can put that on a plot. So this is something that I ask my students. Hence I have the no for exam. You can plot this up, and you can see that if you know the number of parent to daughter isotopes, you know something about the half-life, which you measure into a lab or you look up in a table, then you know something about the age of the specimen that you're looking at. Let's imagine how that's done. So here is a woolly mammoth. That woolly mammoth is running around 40,000 years ago, and it is eating plants. Woolly mammoths and modern day elephants are herbivores, right? So they're eating leafy greens and plants and things like that. Those plants have a certain amount of carbon-14 in them. Carbon-14 is the radioactive element of carbon. It's an unstable version of carbon that gets made in the atmosphere through interactions with cosmic rays, but it's always around, and it's always abundant in the plants that this woolly mammoth is eating. So this woolly mammoth has some amount of carbon-14 in them at all times while they're alive. But obviously when they die, or when they're used for food by early humans, then they're no longer consuming carbon-14. And carbon-14 has a half-life on the order of about 5,200 years. And so that carbon-14 starts to decay into the parent nitrogen-14, into the daughter nitrogen-14. The carbon is the parent. And so we can go to very fancy instruments like you see on the right-hand side there. That's a nice big mass spectrometer with an accelerator. And we can figure out what the isotopic ratio of parent to daughter is, carbon-14 to nitrogen-14 of this woolly mammoth, and we can figure out that this woolly mammoth was on the order of 40 or so thousand years old, or 35,000 years old, or whatever the number may be. But now we're actually getting an absolute number. This is really super useful information, as opposed to just relative dating, which is also useful information, but now we're actually assigning a number to this. When you're picking or you're figuring out what system to use, you have to think about what you're dating. So remember, we were just talking about carbon, and that carbon has a half-life of on the order of 5,200 years. Well, for somebody like me that did a lot of work on early Earth, for example, so I'm looking at rocks that are on the order of 4 billion years old, that wouldn't really make sense, because if it has a half-life of 5,200 years, then within just about 10 or so half-lives, there's no more carbon-14 left for me to actually analyze. So it decays away and it's gone. So for me, what I used, for example, when I look at early Earth, I like to use the uranium-lead system that you see in the middle there. 238 uranium decays to 206 lead, and that has a half-life of about 4.5 billion years. Well, that's great, because the planet's about 4.5 billion years. That means half of the original uranium-238 should have decayed to lead. And so because the planet has only gone through about 1 half-life. And so it depends on what system that you're looking at. You can pick different decay systems to kind of match what you're trying to date. And ultimately, you're going to use both methods, because not all rocks are datable. For example, you can see that there's a Paleocene sandstone there, and it doesn't have an age. The reason it doesn't have an age is because it's a sedimentary rock by definition. It's a sandstone. It's made of little bits and pieces of other rock that were stuck together and lithified into this sandstone. So if I try to date it, I don't actually know I'm not dating the time period when my sandstone formed. I'm dating the little bits and pieces of other rocks that were fed in to make this sandstone. And so we are going to essentially be using both relative and numerical dating when we have a package like this, because not all rocks are conducive to numerical dating. And so when we put both of those bits of information together, we can really come up with a real concise idea of what we're looking at. Even if these are sedimentary layers or igneous layers, we apply all our principles of relative and absolute dating, and we have a pretty good idea of the history of these large packages of rock. So dating some of the oldest rocks, the book that we like to use, and really almost every textbook that we have now, says that the oldest rocks on the planet are about 4.3 billion years old. We do have now individual zircons that are significantly older, so we don't really have any rocks from the Hadean, but we do have a lot of zircons. And in fact, I would bring some into class that I had from my PhD thesis, and they would be able to hold 4.3 billion year old zircons. So these are very, very old, older than any other bits and pieces of rocks that we have on the planet. But there's a cool YouTube video that I like to put up a link to that you guys can pause real quick and put into YouTube, that talks about some of the dating of the oldest rocks on the planet. There's other ways, obviously, to get numerical ages. You can do things like tree rings. We can count layers in glaciers or in sedimentary packages. So there's quite a few others. We'll touch on some of these when we start touching a little bit on climate. But these tend to be used for more recent times. If we're talking about deep time, which is the name of this lecture, really we're looking at isotopic systems. We're looking at radiometric dating. But we'll talk about some of these other ways to get some numerical ages in environmental information when we start discussing climate. All right, well, thanks again for tuning in. If you enjoy this, please subscribe to this channel. I'll be putting out these. I try to put these out weekly. It tends to be maybe more every other week. Again, please follow me at Matthew Wielicki on Twitter. Subscribe to my Substack, irrationalfear.substack.com. If you can, please become a paid subscriber. There will be free posts as well. So if not, just subscribe and enjoy the free posts. But if you can, it's a great way to support independent reporting. And thanks again. Have a great day.